So next speaker is Markus from BlockScience, and he will talk about cadCAD, and also he's going to demonstrate using how to use cadCAD, right?
Yeah.
Okay. And also just letting you know, we got the pizza, so if you want to grab some slices, just go ahead.
Hello everyone, my name is Markus. I'm a research engineer at BlockScience. I work part-time at BlockScience and I'm a data scientist on part-time, and I work as a data scientist at the Brazilian audit institution, where I use public data sets to sort of do risk assessment and direct the work of the office. So I'm going to talk to you a little bit about cadCAD. So I don't have to talk too much about, since we're in token engineering meetup, I don't have to talk too much about the need for token engineering, I think. We've all heard the analogies. We've been building bridges since forever, and no one builds bridges and then just says, okay, start driving on these bridges and let's see what happens. But this is basically what we see most of the times with people building decentralized applications, right? And I like this analogy by Alexander Volkin, where he says that these decentralized applications are basically robots that we're putting out in the world and saying, let's make this robot walk in the middle of this crowd, and this robot will be kicked in, lifted up, drawn in acid, and we have no control over what's going to happen once that robot is out there. Everyone can do anything with it. Everything that we let them do with it, everything that we bake into that robot, every kind of mechanism that we add to that robot for people to interact with it will be done. So we have to carefully choose what can be done with it and what cannot be done with it, so that we can have that robot fulfilling its objectives. So we're building cyberphysical systems which have economics in the loop, humans in the loop, are intelligent, are real time, have all these properties. And what we saw at BlockScience is that one of the missing pieces of building this was in this yellow area here. We needed improved design tools that would enable a better design methodology, right? Doing things, really applying engineering principles to creating and designing this decentralized applications. So we came up with this framework, where we start creating, we have these 4 phases basically, where we have a state update framework that defines the system we're designing, and we start by modeling it as stochastic differential equations. And we have, on the user actions framework, we have a population level agent behavior, where we model the populations that will interact with our system as subgroups of populations with different characteristics, right? And we do some computer-aided design decisions on this first level. Then we start fine-tuning by keeping the same stochastic differential equations that we had before, but now we start doing some agent-level population and start refining things a little bit more. Once we're past that phase, we start emulating the chain code in something like a private net first, and using those same agents models that we had. And then we finally go to public testnet, and we replace those agent level models with real agents on this test, right? And at each one of these points, we can sort of go back and reiterate on what we had and see if what we modeled was right or not. What does the data tells us that we collect on the second phase? What does the data tells us that allows us to refine what we had before? So the way we go about this is we start diagramming, basically, before we start diving into any kind of code. And one of the diagrams that we use frequently is this states and flows diagrams, where we basically have each one of the state variables in our system that we're designing, and the mechanisms that make those state variables change, right? So this is from early work that we did on Simon's Autonomous last year, where we have the R tokens being generated by a mechanism. This same mechanism also takes some reward from pool ether and sends it to a caller address. There's a bonding process that mints new SOL tokens, and so on. So basically, you have each one of these diamonds here as the mechanisms, and state variables being incremented or decremented according to the mechanisms, right? Once we have that, we move into a bit more detailed diagram that helps us build the cadCAD, the actual cadCAD model, right? So we have those same state variables that we had there. We have the same state variables here. You have to think about this in terms of what are sort of endogenous variables to the system that you're designing and what are exogenous variables to the system that you're designing, things that happen outside of your system and that are outside of your control. And then you can start thinking about what the mechanisms are, what are the sort of the interfaces that you're going to provide to the users of your system, which will update those state variables, right? So basically the diamonds we had in the previous diagram. And for the external variables, the exogenous variables, you model these exogenous processes that will make the changes in those variables. In cadCAD language, what we talk about, what we refer to are state update functions. So all those mechanisms that we talked about in the previous slides, they are converted in cadCAD into state update functions. For each pair mechanism state variable, you have one state update function in the code of the model. And then the mechanisms are triggered by what we call policy functions, which need to be of three types. You have some kind of exogenous policy function that drives the exogenous processes. You have the user policies, where you model how your users are going to behave and what they're going to do with the mechanisms that you have made available for them. And you have some kind of internal policies where the system itself is changing based on its internal state. And after all that, you get some key indicators that you're going to be looking at in order to make decisions as you design your system, right? The key indicators are derived from the state variables. On top of that, that whole thing is looped in time, right? So we do that iteration at each time step of the simulation. We're simulating time in discrete time. So you start with the system data, those state variables, and then only part of it is observable by the users. The users look at those data, at that data. They have an internal system of beliefs. They have some kind of a random external process, and they have what mechanism they can interact with, and the actions that they trigger on the mechanisms. Once they trigger the mechanisms calculate the new value of x, the system state, as a function of the current system state and the user action. Another way to see it is like this. We have the current state of the system here, the policy functions, be it the system policy functions or the user's policy functions or the exogenous ones. All these policy functions are going to be aggregated and sent as an input to the state update functions, which will also read from the current state of the system, and based on the current state of the system and the aggregated output of the policy functions, they will calculate the new state of the system, right? Each one of the state variables. So what I wanted to do was show you a little bit about what we're doing with the Uniswap case. We have a couple of tutorials, a few tutorials on the cadCAD repository, where we do this toy model of robots picking marbles from boxes and putting the marbles in other boxes and things like this, which is a simple model for people who are not familiar with modeling to understand. But we started working on this Uniswap model, which we think is a lot more interesting, and we have some real data on it that we can model from. So I think it would be interesting to talk a little bit about it. Everyone's familiar with Uniswap? Yeah? Okay, so I don't have to explain how it works. Good. So basically, this is what we do when implementing the state update functions, right? Uniswap basically has four mechanisms. You can add liquidity to a pool, remove liquidity from a pool, exchange token for ether, or exchange ether for the token, right? So those four mechanisms are represented in these four boxes here by three state update functions in the liquidity mechanisms, because each one, remember, each state you need one state update function for each one of the state variables that you're updating, and we're updating the ether balance, the token balance, and the supply of uni tokens. And you have two state update functions for the trades, because you're either adding ether and removing dye or vice versa, right? We set the initial conditions of the system. So Uniswap, when Uniswap was first deployed, it started with 5,900 dye and 30 ether. And the supply of Uni was the same as the supply of as the balance of ether. And this is how Uniswap implements their fee model, their fees. So basically, this means that 0.3% fee will be collected. And then we can backtest. So basically, we just those functions just implemented Uniswap, the smart contract, in a Python version of it, according to the cadCAD language. Now we need to know if we implemented it correctly, if the model is right. So we need to backtest it. What we do is we download the data from using Google BigQuery. We download the data for everything that happened on the Uniswap Ether DAI instance since it was deployed late last year. So we have the first time that any liquidity was added, and then when some ether was purchased from the pool and some token was purchased from the pool, and we have about, I don't know, a few hundred thousand data points. And then we create a policy function that simply mirrors that history, right? So this is going to input to feed our model with the same inputs that Uniswap was fed along the course of its history, right? So if the event is a token purchase, we say that the amount of ether sold is the same amount that's showing on that on the table there. And if it's token sold, if it's an ether purchase, then we say that the input token sold is the same amount of tokens that was there, and so on. And then we compare, right? And we can see here that around 99.9% that we can see that what is one-to-one when we compare the ratio between what the ether balance of the model was at each point in time and the ether balance of the real Uniswap instance was. It's basically the same every time. But we remember our diagram here. We are not doing this right now, right? What we're doing is we are not feeding our policy functions with any of the current state of our models. We are inserting into the state update functions historical Uniswap data. So this means that we can't really play around with this model as it is. If we increase the fees of this model, for example, it tells us we can't reach any conclusions about that increase in fees because we cannot say that the same things that happened would have happened if the fees were different, right? So we need to move from this to this. We need to create policy functions that read from the system state, read from some external price reference, and then input trigger the mechanisms and send that information as state update functions, to the state update functions, right? So a simple way to do this would be to model the users as having a simple goal, to move the price of Uniswap, the spot price of Uniswap, to the same reference price that they have external, the same external reference price that they have, right? So in this simple model, what we did was we created a function that said that returns how many tokens they have to send to the smart contract to get a certain amount of tokens in return, so that the final price is the external reference. And the external reference that we used was the external reference at that moment according to Uniswap. So basically what we're modeling here is what would the system behave if every trader on Uniswap was an arbitrager? Because that's what arbitragers are going to try to do to Uniswap, right? They're basically trying to buy cheap on Uniswap to sell for more somewhere else. So they want to bring the price of Uniswap to the same reference price that they have, the external reference price that they have. And again, we backtest, and we see that the values are the same.
Can I ask a question?
Yeah.
Well, I guess this is a distribution, yes?
This is the box plot. Yeah, it's basically a
So
distribution.
they're
So
not the
what
same
these are outliers. So basically, when you look at the distribution here, it's something like 99.9% of the time the value is the same.
Why do we have outliers?
Because the model is not perfect. There are some simplifications in the model. I can talk to you a little bit about this, the simplification that we made and why it creates some differences. But then when it really gets interesting, it's when we start to do some agent segmentation. And that's where we are, that's the point where we're at now. We want to improve, we want to sort of make this user segmentation more sophisticated. What we did here was a very simple heuristic where we try to identify from the past of Uniswap if that trade was made by an arbitrager or by someone who just went on Uniswap's website and said, I want to sell 10 DAI, or I want to sell 1 Ether. The simple model that we have here is basically based on round numbers. We're assuming that convenience traders, someone who goes to the Uniswap website, they will not type in 18 decimals to trade something, but arbitragers will probably do that, right? Again, models. All models are wrong, some are useful. You all heard that before. It's something interesting for us to start playing with, but we can definitely improve on that. And then we say that arbitragers are always going to arbitrage as long as it's their profit is above a certain threshold, a certain fixed cost. And convenience traders, those guys that go to Uniswap website to trade, they will trade as long as the slippage that they suffer is not greater than the slippage that they actually suffered by a certain amount. So we set this parameter here. Additional slippage tolerance for the convenience trader, arbitrage fixed cost in Ether for the arbitrager. And then we can do some parameter sweeping, where we just, in cadCAD language, what we do is we modify the parameter dictionary that we had before, where all we had was, we said the fee in Uniswap is 0.3%, and we changed that to say, test for me what it looks like with 0.3%, 1%, and 5%. So cadCAD is going to run 3 simulations out of this, and give us a data set from which we can calculate those key performance indicators that we had there, right? So this is the returns of the liquidity provider under those 3 different parameters: 0.3% fee, 1% fee, and 5% fee. And what's interesting is that in this specific example, with the parameters that we set and the simplification that we made, you can see that the blue line is the 0.3%. Right? Is as what Uniswap really was, what the liquidity providers actually got. If we increase it to 1%, it would increase the revenues, the returns of the liquidity providers. But increasing it to 5 starts triggering those thresholds that we set on the arbitrager and the convenience traders, and you start no longer getting trades that you had. So you start forfeiting, sort of giving up on some of the revenue. And the returns diminish. So you basically show that you can increase fees for as long as you want. You have some limits on the model, right? So this is the cadCAD community forums. Join us there. Let's discuss. Let's talk about this a little bit more. Everyone's welcome. We're still a small community, but fast growing. Hope to see you all there and talk a little bit more about this. Thank you.
Any questions?
Yeah, so, like now this is mostly being used to like model smart contracts. Could you use the same tool to model other types of systems, or is it only intended for smart contracts?
No. This is intended for. This is a general purpose thing. We have clients in BlockScience. We have clients who have nothing to do with crypto, traditional business, where we use cadCAD to model their business.
What kind of stuff is that?
Sorry?
What kind of things are those?
Oh, just regular 3-sided markets and platforms and things like this. Any system basically. This is general enough that you can plug any system on top of this.
But is it mostly focused on markets, or you could do other things as well?
You can do anything. You could model like a I don't know, a tank or
I mean,
chemical plant, anything.
Yeah, but I mean, it has to be like better suited for some category of things rather than everything.
I can't say agree. I think
Or
it's,
at least some
it
things
really
would be
depends on the
easier.
user. In my opinion, it's general enough that it really depends on who is using it. I would not be able to use it to model a chemical plant, but a chemical engineer would certainly be. Cool. Thanks.